Start. So I want to double check. Can the people out there hear me?
Yes, I can hear you.
Okay. So I'm Shamit Kachru. I'm a theoretical physicist at Stanford, and I'm a member of the Simon's collaboration on ultra quantum matter. Welcome to our first virtual meeting of the collaboration. I'm today's moderator, and I'm going to start by introducing our fearless collaboration leader, Ashwin Vishwanath, who will say a few words about what we do and why.
Thanks, Shamit. Let me share my screen just to make sure it's all working. Okay, so thanks everyone for being here. We're really very happy with the response, and we'll be telling you a little bit about topics related to ultra quantum matter. This is our first virtual meeting. And we were supposed to have a meeting around this time at Stanford, which of course we couldn't do. So we've converted into this virtual meeting, but we hope it will have the same flavor, at least as far as the science is concerned. So the collaboration is a group of 17 physicists, theorists from different backgrounds, condensed matter physics, high energy theory, AMO, quantum information. And it's really been kind of a wonderful experience to get all of these different perspectives together. My job today in the next few minutes is to say a little bit about the kind of things we're interested in and to place some of these topics in perspective. Okay? So the first question that always arises is what is ultra quantum matter, with Simon's collaboration on ultra quantum matter. And we're really interested in states of matter, many particle systems that are of course quantum mechanical, but also highly entangled. So I think the best way to start is to give an example, the quantum Hall states that we are all very fond of. That is essentially a highly entangled state of quantum matter, and the kind of things that we will be interested in are related more to states like that as compared to, for example, more classical states. So although solids are composed of quantum mechanical particles, they have a very efficient description in terms of a classical order parameter. So that's not something that we would include under ultra quantum matter. Another example of something we would not include as ultra quantum matter is that, unfortunately, we don't have much to say. And we'll be focused more on these highly entangled quantum states. To give you a little bit of a breakdown of the different talks and to group them together in a way that is maybe a bit more structured. The simplest kind of highly entangled states are gapped states of matter, like these quantum Hall, fractional quantum Hall, or integer quantum Hall states. This is the amazing phase diagram that experimentalists have seen in the fractional and integer quantum Hall states. And in fact, we'll have talks related to that. On the left, I have the title and the speaker, not necessarily in chronological order, rather in terms of intellectual kind of cohesion. And when you take these gapped, highly entangled phases, go to higher dimensions, go to 3 dimensions, it turns out the things get even more rich. We don't quite have the precision experiments that we have in 2 dimensions in the fractional quantum Hall phases, but theoretically, we see that there's an enormous variety of such states, for example, fractons, and we'll have a talk about fractons and relating them to the kind of theories that appear in the quantum Hall regime. You can also talk about gapless highly entangled phases. In fact, these quantum Hall states we talked about, they emerge from a gapless phase, the Hassel-Landau level, and we'll have talks about that and how these other states emerge from these gapless entangled phases. We'll also have talks about the strange metal. In fact, that'll be the first talk of the session today. And that's another example that falls under this category. Of course, if you do have ultra quantum matter, this highly entangled states, important question is how do you know, how do you tell? And probes of these phases are as important probably as realizing them, and that will be the subject of one of the talks. And finally, we've talked about entanglement quite a bit. In fact, we have several talks on quantum entanglement perspectives, and we're grateful to Steve Schenker for joining the meeting, and he'll be giving us a talk about questions related to quantum information and gravity. At this point, I think I'll turn this back over to Shamit to start the sessions, and we hope this will be a stimulating meeting for all of us. Shamit.
Great. So please stop sharing your screen, Ashwin. Okay, so we're about to start the session. Let me outline some logistics. The talks will be half an hour long, but then there are 10 minutes of questions afterwards, so the full extent is 40 minutes. Let me explain mechanics of questions. The collaboration members and a few others are panelists here. If they have questions during the talk, they should just type into the chat they want to ask a question, and I'll indicate to the speaker that there's a question and they can ask it. For audience members who are attending but are not members of the collaboration, what you should do is type questions you have into the Q&A, and at the end of the speaker's allotted time, we will open it up to those questions, and I'll read the questions that you've asked, and we'll get some sort of response, hopefully, until we reach the 40-minute limit. So with those logistics hopefully clarified, let me turn it over to our first speaker. We're delighted to have Subir Sachdev, who will tell us about the time reparameterization soft mode. So Subir.
Okay, thank you, Shamit. So hopefully my screen is being shared now. And let's see. All right, so everything is looking okay, Shamit?
Yes, it looks great.
Yeah, okay, all right. So, so I'm going to be talking about the time reparameterization soft mode. This is actually a mode in gravity of a certain black holes, just ordinary Einstein gravity. But it was, curiously enough, first discovered in the context of the SYK model by Maldacena, Stanford, and Kitaev. And so, so my focus here will be on consequences of time reparameterization soft mode in condensed matter systems, where it turns out to play a rather interesting role. I think some of the things that Steve Schenker will talk about this afternoon are more on the gravity side and probably tangentially connected, but I'm not sure. Okay, so I should mention some collaborators here. So I'm going to need an earlier paper, which is not about the soft mode, in collaboration with these people. And then the soft mode paper more recently is with How You Go in Yingfei Gu. I see a little time delay between what I'm seeing and what's on your screen, I think. This is a bit unfortunate. I don't know what's going on. Right now, do you see pictures of How You Go? No.
No, we see four different collaborators right now. And now we do.
There we go. Okay. Right. Okay. All right. So the condensed matter motivation is the following. So there are many experiments, which I will not go through today, in which if you measure the resistivity down to low temperature over a certain range of densities, it has the behavior shown here, where the resistivity goes to a constant plus a correction that's linear in temperature. And really, we have no such model, which exhibits this behavior in the limit of zero temperature. Naively, you might think, well, everything is linear to first order, but the point here is we're talking about a gapless state, and there are numerous constraints on how transport works. And if you take any generic critical gapless state, you will not get a linear resistivity. One of the things I want to argue here is that in certain classes of models in high dimension, you do generically get a linear resistivity, and it's a direct consequences of this time reparameterization symmetry. Okay, so there'll be two key ingredients in what I'm going to talk about. The first one is fractionalization. So this is a very common phenomenon now in ultra-quantum matter, especially in the fractional quantum Hall effect, where you imagine the electron operator C alpha breaks up into some spin-ons, say here F alpha, which is a fermion, and the boson, which carries the charge. And one consequence of this fractionalization is that there's an emergent U1 gauge invariance, or U1 gauge symmetry, which then controls the effective field theory of the F alpha and the B. And there's been literally thousands of papers exploring the consequences of those. And typically you get also a gauge mode, a low energy gauge mode, which has interesting consequences, but so far has never really been shown to cause the ubiquitous experimentally observed behavior of linear anti-resistivity. So, but I'm going to still need fractionalization. It's in what I'm going to talk about. The second important ingredient will be the aforementioned time reparameterization symmetry. So this is just an effective action for the low energy fluctuation, in which if you reparameterize time from tau to any f of tau, then in the nuke set of coordinates, you still get essentially the same theory, at least at low energy. And one curious fact is that this is not some peculiar symmetry. In fact, it's present in essentially the known models of non-Fermi liquids. In particular, models where you have quantum matter some variable density, but without well-defined quasi-particle excitations. So in fact, one of the best known models of a non-Fermi liquid without quasi-particle excitations, say, is one that appears, for example, in the nu equals 1/2 state of the fractional quantum Hall effect, which I think Senthil will talk about. So here you have a model of a Fermi surface coupled to U1 gauge fields A, and you're interested in the low energy excitations. So if you focus on these antipodal points here and look at the low energy spectrum, it turns out that the dominant component of the gauge field that you need to worry about is the one that's along this direction. So if you write down the low energy in the vicinity of this point of the Fermi surface and that point of the Fermi surface, you get an action that looks like this. Where you've got a dispersion for this fermion on this side, and dispersion on the minus fermion on the other side. They couple minimally to the gauge field, and it turns out there's only a certain derivative of the gauge field along this direction that matters. The other one is not important. Okay, so this particular theory is studied greatly, and what we know is that at low energies, there seems to be a critical state that's realized. And you can actually understand the structure of that state quite easily. You take this low energy theory and look at its invariance in the rescaling. So if you rescale x by s, then because of the mixed derivatives here, you have to rescale y by square root of s. And let's just imagine you rescale time by s to some power z. And then you look for some kind of fixed point of this theory. And what you find is that you have to then look at what happened to the gauge coupling, which is the only coupling here. And this gauge coupling remains in.
Is anyone hearing Subir?
I'm not hearing Subir, are you?
No.
I'm not either.
And the presentation seems to be frozen.
Okay. Let's try to contact him. Ashwin, do you have Subir's phone number?
I got him on the phone, so it'll just be a minute.
Okay.
I think he didn't realize we couldn't hear him.
Right.
Can you hear me now?
Subir's re-logging in now? Yes.
Sorry about that. Can you hear me now?
Yeah, we hear you.
So you didn't hear any of the talk at all?
We heard you through where you were saying z equals 3/2, the slide with the scaling.
Oh, great. Okay, good. That's not so bad then. Okay. Yeah, you need to make me a host.
Sorry.
This Bluetooth.
I'm making one of you a co-host.
The one, yeah, let me see.
Is it the right one, or I'll do the other one too?
Do the other one, please. Yeah.
Okay. You're now both co-hosts.
All right, so sorry about that. So I was here. See, so this is the correct place to start, Shamit, is that correct?
That is the correct, yes.
All right, so then I said that, well, because the time derivative term here is irrelevant, you can in fact make S a function of time. And therefore, this particular theory is invariant under time reparameterizations, where tau goes to f of tau. So this is just to show you that even a generic theory of fermions coupled to a gauge field has a time reparameterization symmetry, although there's been very little work on understanding what its consequences are. And this is something we are working on. But now to begin the main part of my talk, I want to discuss. Yes.
Yeah, can I ask a question now? So I mean, that's a very interesting remark. Actually, just an ordinary Fermi surface coupled to a boson mode theory has the reparameterization symmetry. But actually, I mean, the standard way of dealing with this is to integrate some boson and get some bubble diagram, but that actually will have a frequency in the Fermi self-entry. So would you say the reparameterization mode is actually, I mean, symmetry is actually broken? Or spontaneously broken?
So yeah, no, that's a good question. So you can't do it that way. So you really have to start where you have to, if you take one mode and integrate it out and get a long range interaction for the other mode, then you've immediately lost the reparameterization symmetry. It's really crucial that you treat both modes self-consistently. And that's kind of
the standard way is just not correct.
Well, I mean, if certain large n expansions will be all right, we'll have this reparameterization symmetry. You may have to still worry about the time derivative, but if you do what I said earlier, that you just integrate out part of the degrees of freedom and with some long range interaction that you keep fixed, so you have some power of omega in your theory, then at that point you lose this reparameterization mode.
Mm-hmm.
In fact, that's also coming back to the next problem. That's kind of the difference between the SYK model and say a Kondo model, a multi-channel Kondo problem. In a multi-channel Kondo problem, you have an impurity coupled to an environment, and you integrate out the environment, you get some long-range interaction for the impurity, and that model does not have time reparameterization symmetry. In the SYK model, the environment is the impurity, and that's why you get the time reparameterization symmetry. Okay, so good point. All right, so my perspective here is to use the SYK model as just an interesting solvable model that has the soft mode. But really, I believe there's a much larger class of systems which you can't solve exactly that do have this soft mode. And there's a lot of reason for that, for justifying that. Okay, so this, just to remind you, is the SYK model with random 4 fermion interactions of n fermions with n possible labels, which I call A, B, C, D. And in the large N limit, this model is described by essentially this particular simple diagram here, where sigma, okay. All right, so I'm not sure why my mouse is not working, but anyway, so the diagram on the lower right where sigma goes as G cubed. All right. Okay, so now let me just remind you and focus on the crucial properties of the SYK model, which I believe are generalizable to many other systems. So this, first of all, this is some kind of critical state without quasi-particle excitations. And it has a very nice property that the critical state has a variable density. It's not fixed at a given density. It can be anywhere, a range of densities around half filling. Another property is that the entropy doesn't vanish in the 0 temperature limit. Here we have to be very careful that the n goes to infinity limit is taken before the t goes to 0 limit. And this implies that really this entropy is not due to a ground state degeneracy, but just in the exponentially small spacing between the low energy levels. If you perturb the system and look for its equilibration, then you get this Planckian time where the equilibration time is about 1 over temperature, but it doesn't immediately transfer into a transport time, as we're going to see, but this is at least showing you that the characteristic time scale is just temperature itself. Right, so as I mentioned earlier, another important property of the SYK model is the time reparameterization soft mode. Furthermore, this time reparameterization symmetry is softly broken at low energies to a conformal symmetry. And that's a generic feature of these 0-dimensional models. And one consequence of that is that if you look at the low temperature behavior of the entropy, the correction to the term I had in the previous slide is linear in temperature, this gamma T term. And this comes from an effective action from the soft mode, which is the Schwarzschian. So I won't go into any details of this, but the general lesson here is that if you look at fluctuation corrections from the Schwarzschian, and this is already in the large N limit, I'm not looking at 1 over N corrections. Those corrections go linearly in temperature, in the entropy, and also actually in many other observables. And that's really what I'm going to exploit in the rest of my talk. Okay, so why is there a soft mode? Well, very similar reasons to the Fermi surface coupled to gauge field. If you take these equations that I wrote down earlier for the Green's function and self-energy of the SYK model, then in the lower Gini limit, where the Green's function goes as 1 over square root of z, you find that the I omega and the chemical potential terms renormalize away and can be ignored. And the equations in the, I don't know why my pointer is not working. Can I just try one more time? This is a bit annoying. No, okay. These equations on the top reduce to the integral equations written down at the bottom, and it's easy to see that these equations here, as pointed out by Katev, are time reparameterization invariant. Okay. All right, so another property related to this Schwarzschian mode is the out of time autocorrelator increasing at the maximal Lyapunov exponent of 2 pi t over h bar. This is not something I'm going to use, but it's been the main use of the time reparameterization mode so far in the literature. And finally, one thing I will need, which is somewhat specific to the SYK model, that's why they have these dotted lines around the number 6. If you endow these fermions with spin, then in this particular 4 fermion model, the spin correlations decay as 1 over tau, and that'll turn out to be very crucial for the actual application I'm going to talk about. All right, so that's my rather rapid summary of the SYK model and its key properties. And now we want to use those properties and see where they emerge in other models, in particular models where you can talk about transport. So one way to extend the SYK model to include transport is to take a lattice of SYK model. And here I'm showing a picture which is rather similar to a model considered by Leon Valens and collaborators, where each circle here with the colored dots represents an SYK model. Here, think of the colored dots as some orbital labels in some big atom. And then you allow for hopping, either random or non-random, between these big atoms. So this is also another model that's solvable in the larger limit. It's the same set of equations, except you have to include the momentum dependence. And what you find in this model is quite interesting. What you find, you do get a resistance that goes linearly in temperature, but not down to 0 temperature. So this hopping introduces a scale, which is t squared over u, below which, in fact, you lose the interesting SYK behavior and you cross over to a Fermi liquid. But in the intermediate regime where the hopping doesn't destroy the incoherent behavior on each quantum dot, you do get linear temperature resistivity. So that's quite interesting for many purposes. But the goal I've set for myself here is to really find a model where this holds all the way down to 0 temperature, which doesn't happen here. It's only over some intermediate temperature range. So to fix that problem, as I said in the beginning, I'm going to have to introduce another ingredient. And that other ingredient is fractionalization. You really need to take a model where you have more than just electrons with these random interactions. Okay, so the model I'm going to take is a very, very familiar model in this manner, just the TJ model. So in this case, you have electrons moving on some lattice with the constraint that the number of electrons on each lattice side is always less than 1 or equal to 1. And there's some density of holes, which I'm going to call P. Oops, sorry. So on each side, then you have 3 states, the empty state, the spin up state, and the spin down state shown at the bottom. Somebody has raised their hand, or I'll just wait for Shamit to interrupt me if I have to respond to that.
No, Subir, please continue. If there are questions, please type them into the Q&A.
Okay. All right. So that's the TJ model in a generic system. Now, of course, that's not solvable. If you could solve it, we'll have nothing to do. That would just, and we think describes so many interesting experimental phenomena. So we're going to take a certain limit, which I believe captures some very interesting physics. So there are two extensions we're going to take. First of all, we're going to take this lattice in high dimensions. So Z is the number of coordination number of each site, and we take the large Z limit, a small z. And secondly, we're going to take the exchange interactions and make them random. That just simplifies the equation, and the second approximation is not believed to be essential, but it makes life a lot simpler. So let me just talk about that. All right, so this is the model we're going to try to solve. It turns out even with these 2 limits, it's still extremely difficult. It reduces to a very complicated set of DMFT-like equations that have to be solved, which people at the Flatiron Institute are working on. And I'm going to mention some of the Flatiron results in the end of my talk. So we're going to have to make certain further approximations to make analytical progress, but those, I believe, don't really change the generic behavior that we're going to describe. Okay. So the way you deal with this constraint here, that C dagger C has to be less than or equal to 1, is by using what sometimes was initially called the slave boson method, or fractionalizing the electron. So you take the electron C alpha and write it as a product, as I said earlier, of a spin-on F alpha and a holon B. And so these three states shown here in the middle now correspond to a B particle present, that's the empty state, or the F particle present in the spin up and the spin down state. And so there's a constraint that F dagger F plus B dagger B equals 1. And that, of course, introduces the gauge invariance. So this is one way to formulate the theory. And then you find, if you make this decomposition, there's a certain democracy between the T and the J term. Both the T and the J term become now 4 particle terms. And that's good because it's the 4 particles term that are really driving the SYK behavior. So that's, roughly speaking, why I need the fractionalization. We want these two terms to compete with each other. We don't want one term to always win at low enough temperatures, which is what happened in the original SYK lattice model. And in some ways, it's also very useful to think of this as a superspin model. You have a spin with 3 components: the empty state, the up state, and the down state. And these 3 components can be rotated in this, not in SU3, but as SU1 bar 2. So in this picture, you think of the 2 spin up and spin down state as fermions and the empty state as a boson, and that's why it's 1 bar 2. However, there's nothing sacred about this way of doing it. You can do it the other way too. You can make the spins bosons and the empty state a fermion. And then this would become SU2 bar 1. And if you solve the theory exactly, both methods should give you exactly the same results. And in fact, that's what we're going to do. We developed an RG procedure in which you could use either method. And both give you exactly the same results. And that's really one of the strengths, that you're taking the gauge fluctuations into account exactly once you've taken these large dimension and limit. Okay, so what do you get from that kind of RG analysis? So what's, I should mention that these 2 supergroups are actually exactly the same, as they should be, because they're really talking about the same model. It doesn't, you can make a choice of what you call a fermion and what you call a boson. So what you find from the RG procedure is that as a function of P, which is the horizontal axis here, which is the doping, there is a critical point. And roughly speaking, that critical point at 0th order in the calculation is when these 3 states become degenerate. So the empty state, the up state, and the down state have the same energy in this grand canonical ensemble. And what that tells you is that the critical point PC at 0th order is 1/3, which is already quite an interesting thing. The other thing we can show in our RG to all orders in the RG expansion parameter is that the spin correlations decay as 1/tau, just like they do in the SYK model, as I mentioned a few minutes ago. And even the electron Green's function also decays exactly as 1/tau, which is a Fermi liquid-like exponent. So you might think this is some kind of Fermi liquid state, but it isn't, because the spin correlations decay much slower than in a Fermi liquid. The spin correlation in the Fermi liquid would decay as 1/tau squared. So this turns out to be the critical state, which we're going to then look at finite temperature and look at the effect of this critical state on the time reparameterization mode. So, which is in fact present here.
Sorry, Subir, just a quick question. So these scalings come from the fact that F and B both have scaling dimension 1/2, something like that, or?
Let's see. So yes, I believe that's correct. Yeah. So
okay, so that's the point.
Well, but that reasoning that you're presenting, which I'll present in a minute, really is a reasoning that comes from the a large M limit, where you have to take one of the 2 representations and take a large M limit for SUM symmetry. However, this RG calculation doesn't use that reasoning at all. In fact, you don't even have to fractionalize the particles explicitly. You have to really integrate over the gauge field exactly, which you can do here because of the 0-dimensional nature of the effective theory. So there's a West-Zimino-Witten term, which you have to integrate over exactly, which you can in the 0 + 1 dimensions. And this really comes from a certain subtle non-renormalization of some kind of, well, I guess is one way to say it, of a field in a Witten model. Yeah. So we got it from very different methods here. Yeah. So it's something we can show to all orders at the fixed point, coming from an exact theory where we don't actually work with the fractionalized particles. It's a very different mechanism, but it's very satisfying that it gives exactly the same answer as the large M theory that you mentioned. In fact, this particular coincidence that these two exponents are the same is something, this exponent 1 over tau was already present in the very original SY model in '93. And it was in subsequent work for the SY model with Matthias Voita that we showed that there's other ways of getting it from using an RG argument without using the large M limit. Okay, I'm probably dwelling on that too long. So let's move away from the critical point. So on the higher doping side, what you expect, since you have more holes, is that the whole state will become lower in energy. And now here the logic is, when you have something that's lower in energy, you should make it a boson, because that state wants to condense, and so why don't you help it along? So what that would mean here on the right-hand side, it's better to make a choice in any approximate theory of choosing the representation, which is SU1 bar 2. So you make the lower state a boson and you condense it, and then you see that you get a conventional Fermi liquid with a large density of carriers appropriately defined. The spin correlations decays 1 over tau squared, and it's a Fermi liquid, so C goes to 1 over tau. On the other hand, on the lower doping, on P smaller than PC, it's the spin states that are bosons. So you want to make those spin states at lower energy, so you want to make them bosons. And when you condense, since the bosons carry spin, you get a spin glass. And now the spin correlations decay even slower. They go to a constant, so it's some kind of disordered Fermi liquid as far as charges are concerned. But the number of carriers here are the fermions here, which are density P. So you have then, away from the fixed point, kind of a small to large density change, separated by this deconfined critical point, which has time reparameterization symmetry at low energies. Okay. So as Chenke mentioned,
just a clarifying question.
Yes, please.
Is this symmetry SU21 or SU12? Are they exact through the diagram, or are they explicitly broken on one side or the other?
They're broken everywhere. That's just the algebra of the operators that you use. If you wish, it's only the symmetry of the Witten term. It's not a symmetry of the rest of the action.
And why did you write on the left SU21 and on the right SU12?
Well, so
is that related to the two phases or not?
Well, so what I've written here is that to understand the phases, we have to make some approximation. If it makes some zeroth order theory where things look good, where you're getting the physics of that phase from, you look at what's happening in the RG. What happens in the RG is, if you're on the P less than PC, these spin up and spin down states become much lower in energy. So you make them bosons and you condense the bosons. So because you have two flavors of bosons that you're condensing here on the left-hand side, you call it a SU2/1 theory. On the other side, on the right-hand side, you're condensing one flavor of boson. So that's why it's SU1 or 1/2. They're the same theory. This is just a question of which fields are more convenient to condense and describe the phase. Of course, if you treated it exactly, it wouldn't matter which one you pick, but you don't treat it exactly when you're condensing something. Okay. So this is the theory that Chenke mentioned. This is some large M limit where you take in this case, you make a choice. You work with spin-ons as fermions and holons as bosons. And then you get these extensions of SYK type equations. And then if you look at the spin and the electron, the gauge invariant correlation function, they're exactly what you find from the completely different RG argument. And what this tells you is that these exponents have no corrections to any order in 1 over m of this SUM theory. They're basically the same for all values of m. Okay. So this is just my one experimental slide. There's this recent nice NMR work by Marc-Henri Julien on the cuprates, showing evidence below this P star of around 0.18 of some kind of glassy spin order in the pseudo-gap regime in a high magnetic field when you suppress the superconductivity. And so, this is just some evidence that thinking in terms of some disordered spin-ordered state may be quite reasonable to understand the pseudo-gap phase. Okay, so now we want to go to this critical point, with time reparameterization symmetry and think about what are transport properties. So I already told you what the electron Green's function was. It's just 1 over tau. So if we just compute, and now we're working in the large M theory, the conductivity from the Kubo formula for this high dimensional model, you find that it's just a constant. It's independent of temperature. And the fact that it's a constant is very important because that means we have to go beyond the leading critical theory. We look at corrections to the leading exponents. And the reason it's a constant is because the electrons essentially have the Fermi liquid exponents. And that is in turn related to, really crucially the whole structure of the problem, where you have these self-consistency equations on both the T and the J terms.
Subir, you have 10 minutes left.
Okay, so I'm almost done, I think. All right, so however, this state is not a Fermi liquid, as I mentioned before. The spin correlation decay is 1 over tau. And you would expect in a Fermi liquid that the correction to residual resistivity goes as T squared, which does not happen here. So what is the correction? Well, that's the new calculation by Haoyou Guo and Yingfei Gu. So you take this leading order 1 over tau behavior, that's the sine function in front of the the round brackets that I showed you earlier, but at finite temperature, and you look at its corrections. And what was shown by Maldacena, Stanford, and Kiteev and Sir is that essentially, by extending their results to our model, that the corrections have an extra power of temperature over J, and this is entirely a consequence of this extra soft mode, which has a scaling dimension which is just pinned at 1 because of the structure of this time reparameterization symmetry. And the coefficient alpha G is something that you can relate to the coefficient of Schwarzschild, which is then related to the specific heat. All right, so we just take this particular expression and put it in the Kubo formula, and you get our main result that the resistivity has a correction. At least this is in the large M limit, which is linear in T. I'm out of time, but let me just complete the story by telling you that if you take a more general model, which is a Hubbard model, so this red line is the critical point that I've described so far in a general Hubbard model. There's a critical point here at half filling as a function of U, and this was studied at Flatiron. And in their numerics, they found results entirely consistent with the kind of analysis I presented here. And our analysis can also be extended to this model, where the spin correlation decay is 1 over tau. And numerically, they find a resistivity with hardly any residual linear in T down to the very lowest temperatures that they're able to compute. Okay, so I'm just going to, thank you very much.
Thanks, Subir. So we have a couple of questions from the audience, and then we have time for more questions from the panelists too. One of the questions is about your fractionalized, your theory with the non-Fermi liquid. And the question is from Yashar Komajani, who says, would you speculate about emergent supersymmetry at the QCP? And is there residual ground state entropy? And how does it fit with the third law?
Okay, those are separate questions, but all good questions. So let me go back to our QCP. So here's our phase diagram. I hope you can all see it. So this particular model, does not have supersymmetry, and does not have SU2 1 bar 1 or SU1 bar 2 symmetry. You can imagine a more general model, but you also have random interaction in the density channel. And when you take that model, that has the potential for having a supersymmetric critical point. So that's something that Darshan Joshi has studied, and we are still finishing up that work. But it looks like there is, in fact, no stable supersymmetric fixed point. And the fixed point we have studied here is, in fact, the correct one. The other question was about ground state entropy. So I should emphasize, yeah, there is a zero temperature entropy at this P equals PC. That's one of the 6 crucial properties of the SYK model, which this model also shares, which is also shared by black holes, extremely charged black holes. It's really not, it's not a ground state entropy, it's a zero temperature entropy. So, and it's a generic property of such models. And here, the crucial thing is, of course, the orders of limits. So if you look at this expression here, you first take the n goes to infinity limit at finite temperature before you take the zero temperature limit. If you took the opposite order, you would get e to the s would be the degeneracy of the ground state. That is not the case here. You're really looking at a system. So strictly speaking, it doesn't really violate the second and third law of thermodynamics in that sense. However, it's, it's pretty rare to find a system, even with this order of limits, there are, these SYK type models are the only known system that obey this. And, for these models, I believe it's correct. There's numerically been checked. It works very beautifully. There's even the value of S0, which we computed around 2000 with Antoine George and Olivier Parcolet, agrees beautifully with the numerics. It's just one of those surprising properties of the SYK model, which is, in fact, it shares with all the models I've discussed here, and is again a consequence of this closely connected to this time reparameterization symmetry. And it's also closely connected to the maximal chaos property that Steve will probably explore in some very different directions.
Okay, Ehud Altman has a question for you. Ehud, please go ahead and ask him.
Yeah, my question is, in this Fermi liquid-like critical point with a Fermi liquid scaling dimension, what is the quasi-particle lifetime there?
There are no quasi-particles. It's just that the electron Green's function just happens to have an exponent which is the same as the Fermi liquid exponent.
I see. So the self-energy, like in the S, what is the self-energy frequency dependence, or?
It's just modem. It's a sine omega, just like in the Fermi liquid. So the electron, yes. So so you have to. So you have to look at leading corrections to this, and you get numerically. This has been done by Antoine and people, and they get something that looks like a marginal Fermi liquid behavior for the electron operator.
Okay.
But it's really, it's clear from our computation, you shouldn't think of the electron as a quasi-particle there. It's really been fractionalized. Because if the electron was a quasi-particle, then the spin correlation would be as 1 over tau squared. And that doesn't happen.
Mm-hmm. All right,
okay,
so one more question, or?
Go ahead.
Yeah, right. So here the main contribution, main correction come from the reparameterization correction to the Fermi-Green's function.
Correct.
So is there similar correction that we should worry about in other SYK cluster construction or for strange metal or not? Or this is the only example?
Well, in principle, you should, but they will, since you already get a temperature dependence from the leading term, there will be a subleading correction there. Here, the key point is that the subleading term has no temperature dependence. So we were forced to go to the subleading term. Now, I should say that, so that's that's a feature of the large M limit. So in this particular large M limit, this result here, strictly speaking, only holds when the correction is much smaller than the leading term. That's the limit we can work in.
Okay.
Or if you look at the numerics, which doesn't take the large M limit, that's not what they see. In numerics, they see a linear term which is much larger than the residual term. And that's because they're just working in the SU2 limit. And but that's, analytically, we have no understanding of why that's the case. So that's something we really would like to understand, what happens at smaller m between the leading term and between the temperature independent term and the first correction that you find in the 1/m expansion. Here, this is m of the SUM, not the n of the SYK model.
Okay.
Okay, Subir, there's a question from Joshua Heath. Would it be correct to say that the time reparameterization symmetry is always connected to the breakdown of a Landau-like quasiparticle in a generic fermion system?
Well, I don't know. I can't make general statement of generic fermion systems. I mean, there are, for example, if you take an insulating spin model, it can have, critical fermionic Dirac fermions, for example. There, the time reparameterization symmetry is really part of a much larger conformal symmetry. There is, there is a conformal symmetry, which I guess in 1+1 dimensions anyway has time reparameterization built into it, but not generally. No, I think it's very important that you have a fermion system which is at variable density. So you want a critical state that's at variable density. And the two types of critical states we know at variable density, which can be solved pretty well, are the SYK model and the Fermi surface coupled to gauge field. There's really nothing else, or others that are very closely connected to those. Yeah, so the fact that I had this variable density and this, you're able to expand about these antipolar points so that the time derivative just term that disappears was absolutely crucial. You can't do this for Dirac fermions.
Okay, let me ask one last question and then we have to move to the next speaker. There's a question from Yujin Zhou, who's asking about your critical theory that mediates between the SU2/1 and 1/2 labeled phases. And he's asking, is it obvious that this critical theory really describes the transition between the two phases? It does not seem obvious how to go from one phase to another.
Okay, excellent points. So what we can do is find a fixed point and find the direction, the most relevant direction at the fixed point. So we have a controlled expansion, which we did to 2 loops, and you can go to higher loops if you want. Just a matter of working much harder at P equals PC. And then we can also see what is the most relevant direction. We can see the eigenvector and what its eigenvalue is. And so we just assume that you flow along that relevant direction, and we take the limit where that relevant operator becomes infinitely large. And then we get the 2 phases that I'm showing here. So that's an assumption. I mean, there could be some other fixed point somewhere in between. We don't know. But that's this. So that's what happens here in this RG calculation.
Great. Okay. Thank you, Subir, for a very nice talk.